Today, we are diving deep into something called the CAP Theorem. Now, that might sound a little technical, but trust me, it's this simple but incredibly powerful rule that secretly runs almost every single online service you use, from your bank to your social media feed. It's the reason our digital world is built on a foundation of very tough choices. I mean, it's a fair question, isn't it? We've got all this amazing technology, so why do websites sometimes lag, or show us old information, or just go down completely? Well, the answer isn't a bug. It's a feature, a fundamental limitation. You could almost think of it as a law of physics for the internet. You've probably heard this phrase before, right? It's that classic trade-off. You just can't have it all. Well, it turns out that the giant sprawling computer systems that power our world face a very similar and very impossible choice. And that's exactly what we're going to unpack today. So here's our game plan. We'll start with the impossible choice itself. Then we'll break down the three big guarantees that systems try to make. From there, we'll get into the nitty-gritty of the trade-off, look at how real-world systems handle it, and finally, check out the sequel to the whole idea. All right, let's get right to the heart of it. This whole impossible choice thing isn't just a suggestion. It's a proven concept in computer science called a theorem, first laid out by Eric Brewer way back in the year 2000. And here it is, the CAP theorem in all its glory. Basically, when you build a system that's spread out over a bunch of computers, which is pretty much the entire modern internet, you're trying to hit three main goals: consistency, availability, and partition tolerance. The catch? You can only ever have 2 out of 3. Let's break down what those words actually mean. So, to really get why this is such a tough choice, we first have to understand what the options on the table even are. What are these 3 promises that systems try and fail to keep all at the same time? First up, we have consistency. Imagine you move money from your savings to your checking account. Consistency means that the very instant you hit confirm, your new balance is what everyone, everywhere sees. You, the bank teller, the mobile app, everyone sees the most up-to-date, correct info. No delays, no questions. Next, there's availability. This is simple. The system always picks up the phone. When you go to a website, it loads. When you add something to your cart, the little number goes up. It might not have the absolute latest, up to the millisecond data, but it won't just throw an error in your face. The lights are always on. And finally, there's partition tolerance. Look, modern apps don't run on one computer. They run on hundreds or thousands all over the world. A partition is just when the connection between some of those computers breaks. A cable gets cut, a server goes down. Partition tolerance means the whole system doesn't crash when this happens. And in the real world, this stuff happens all the time. Okay, so we've got our 3 guarantees. But here's the thing. Since networks in the real world are messy and unpredictable, every distributed system has to be partition tolerant. The P is not optional. So the choice isn't really pick any 2 from C, A, and P. The real choice is, when a partition happens, what do you give up? And this is the moment of truth. The network breaks. 2 parts of your system can't talk to each other. What do? Do you stop everything to make sure no one sees out-of-date information? That's choosing consistency. Or do you keep things running, even if it means one user in London sees something different than a user in Tokyo for a few seconds? That's choosing availability. You have to pick. This forces system designers into one of 2 major camps. On one side, you've got CP systems. They prioritize consistency above all else. On the other side are AP systems, which will always choose to be available. Let's see how this plays out with some examples you use every day. Think about your bank. If the ATM's connection to the main server goes down, a CP system makes a tough choice. It will refuse to give you cash because it would rather be unavailable than risk giving you money it can't 100% confirm you actually have. For a bank, being correct is more important than being online. Now, flip that and think about Amazon's shopping cart. It is the classic example of an AP system. When you click Add to Cart, it just works every time. The system's #1 job is to be available for you to keep shopping. Is it possible the inventory count is a half second out of date? Sure, but that can be sorted out at checkout. The user experience is what matters most. So you might be thinking, what about the third option, a CA system, one that's both consistent and available? Well, that would be great, but it only works if you can magically guarantee you'll never, ever have a network problem. And the only way to do that is to run everything on one single computer, which just isn't how massive modern applications are built. Now, here's where it gets really interesting. Over the years, engineers have come up with some really clever ways to live with this trade-off. It's not always the strict black and white choice between one or the other. For instance, a lot of systems used what's called eventual consistency. They basically say, hey, the data might be a little out of sync for a bit, but we promise it'll all get sorted out eventually. Think about the like count on a social media post. It doesn't need to be perfectly accurate for everyone on the planet in the exact same millisecond. Other systems even let developers tune the consistency, demanding perfect accuracy for something important, like a password change, but being more relaxed for, say, updating a profile picture. And believe it or not, the story doesn't even end there. As systems got even bigger and more complex, people realized there was another crucial piece of the puzzle that CAP didn't really talk about. About a decade after CAP, the conversation evolved into something called the CAP Theorem. It builds on CAP by asking a really important question. Okay, we know the trade-off we have to make when the network breaks, but what about the rest of the time when everything's working just fine? CAP breaks it down like this. If there is a partition, you have to choose between availability and consistency. That's the CAP part we already know. But else, meaning when the network is fine, you face a totally different trade-off, latency versus consistency. In other words, do you want your system to respond super fast with pretty good data, or do you want it to take a little longer to double-check everything and give you perfect data? Fast or perfect? Pick one. So what this all boils down to is that building these huge systems isn't about finding some magical best solution. It's about deeply understanding these fundamental trade-offs and then making smart, deliberate choices that actually fit what the system is for, whether that's the absolute rock-solid accuracy of a bank or the lightning-fast, seamless experience of a social network. In the end, what the CAP theorem really teaches us is that in any complex, connected system, perfection is just not on the table. You are always forced to choose. And that makes you ask a really interesting question. Not just about technology, but about priorities in general. When you know you can't have it all, what are you willing to give up?